Hello everyone, and welcome back to my channel. First, thank you to my 10 loyal subscribers. We're growing quickly, and I'd love your support to hit 20 subscribers sometime soon. Today we're talking about Lewis structures. While these seem simple, I found as a tutor that lots of students are decent at guessing what to do when they're faced with a Lewis structure, but have trouble with difficult Lewis structures because they lack a clear system and set of rules to solve these problems. So that's what I hope to do in this video. I hope to give you a system that you can apply to almost any Lewis structure to solve it. So let's start with the 4 basic steps. The first thing we want to do is sketch the basic arrangement of atoms in the structure. So using carbonic acid, H2CO3, is our example here. The first thing we want to do, always, more or less, is put carbon in the middle. Carbon likes to make lots of stable bonds and is relatively electropositive, so it's best suited to go in the middle of the Lewis structure. My next tip is that whenever a molecule contains both O's and H's, we want to pair them up into OH, or hydroxide groups. Since there are 2 H's and 3 O's here, we can make 2 OH groups and have 1 O left over. Next, we'll organize the other groups around the carbon using just single bonds for now. And finally, to make this a little more accurate, we'll spread out all of the peripheral atoms around carbon evenly. And for more details on how to do this, check out my upcoming video on steric number and molecular geometry. The next big step here, once we have this foundation, is to fill up carbon's electron octet using only bonds and no lone pairs. There's only one structure I've ever seen in which carbon has a lone pair, and we'll actually cover it later in this video. So it's always a safe bet to fill carbon's octet with bonds only. Carbon currently has 1, 2, 3 bonds, which makes 6 electrons. So it needs 2 more electrons, which we can accomplish by adding 1 more bond. And we'll have more on exactly where that bond needs to go when we talk about minimizing formal charge in a later part of this video. But for now, I'm going to put that bond in between the carbon and this hydrogenless oxygen. Okay, step 3. Now we have to address the octets of the rest of the atoms in this molecule. And for this, we can always ignore hydrogen because it's unique in that it only ever needs 2 electrons or 1 bond instead of the normal 8. So we're just worrying about the oxygens here. Each oxygen currently has 2 bonds, so I'll just highlight those here in blue. And those bonds correspond to 4 electrons. So each electron needs 4 additional electrons, which we're going to supply with lone pairs because they can't form any more bonds with carbon without exceeding carbon's octet. And they can't form any extra bonds with their hydrogens because hydrogen can only take 1 bond. So let's give each 2 lone pairs. Our structure is looking pretty filled out at this point. So the last step is to check the formal charge. Now first, the formula that I use for formal charge is Fc for each atom equals the number of valence electrons in the atom minus the number of lone electrons, not lone pairs, minus the number of bonds. So let's calculate each atom's formal charge. For this first oxygen here, we know it has 6 valence electrons, and I count 1, 2, 3, 4 lone electrons, and 1, 2 bonds. So that's 0. For this oxygen, it's going to be the same. 4 lone electrons, 2 bonds, 0. And this oxygen is identical to the previous one, so it'll also be 0. Now for the middle carbon, we know it's got 4 valence electrons from the periodic table, minus 1, 2, 3, 4 bonds, also 0. Great. And the overall rule for formal charge is that the sum of the formal charges of each atom must equal the overall charge on the molecule. And since H2CO3 is uncharged, the sum of the formal charges must be 0. And because, as we know, every formal charge is 0, we're good. And this is a correct final structure. Part 2, troubleshooting multiple bonds. In this section, we'll go over what to do when we have double or triple bonds between 2 atoms and issues with formal charge arise as a result. So let's start by talking about carbon monoxide, which is, as I alluded to earlier, the only structure in which carbon will have a lone pair. First, let's use the 4-step method. So we start by simply connecting the 2 atoms by a single bond, that's step 1. In step 2, we're going to fill in carbon's octet. So it's got 2 electrons now, it needs 3 more. So why don't we give it 3 more bonds. In step 3, we now have to address oxygen's octet, which thankfully is already filled by the 4 bonds, so no changes are required. And then in step 4, we'll calculate formal charges. So carbon, it has 4 valence minus 4 bonds. That's 0. Oxygen has 6 valence, and it's got no lone pairs and 4 bonds. So that's going to be positive 2. Now, the issue here is that the sum of the formal charges, 0 plus 2, is 2, but the overall charge on carbon monoxide is 0. So formal charge is too high. And whenever formal charge is too high, the solution is always to give electrons, or lone pairs, back to the atoms by taking away bonds. So if we take our carbon monoxide as it is, remove a bond, and add lone pairs to each atom to compensate, we're left with this structure, in which carbon and oxygen both have 1 lone pair, and there's a triple bond between them. So if we recalculate formal charge now, for carbon it's going to be 4 valence minus 2 lone electrons minus 3 bonds. That's negative 1. And oxygens will be 6 valence minus 2 lone electrons minus 3 bonds. That's going to be plus 1. So minus 1, plus 1. And these, in fact, do sum up to 0. So this structure is good. For our second example, let's look at N2H2. This one doesn't have a carbon, so where do we start? Well, we know at the very least that hydrogens have to be peripheral because they can only form 1 bond. So let's go ahead and start by putting both nitrogens in the middle and give each of them 1 H. In step 2, why don't we treat the nitrogens like carbons and fill their octets up with bonds? So to do that, they've each got 4 electrons right now, 6, 8. Step 3, again, we have no issues since nitrogen's octets are both filled and hydrogen is good with just 1 bond, so no changes are necessary. And now in step 4, we'll calculate formal charge. So for the nitrogen, it's going to be 5 valence minus 4 bonds minus 0 lone electrons, that's plus 1. And for the other nitrogen, it'll be the same. And again, we have the same problem, where formal charge is too high. So we'll use the same solution, replacing a bond with a lone pair. In doing that, we get this final structure, where each N has 3 bonds and 1 lone pair. Recalculating formal charge, we'll have 5 valence minus 3 bonds minus 2 lone electrons for a total of 0. And that is now in line with the fact that N2H2 has an overall charge of 0. So this structure is good. Part 3, minimizing formal charge. So the basic concept here is that we want to minimize formal charge on each atom. The more atoms that are closer to a 0 formal charge, the better. So let's take a look at a great example from nature, the peptide bond. First, I'll quickly draw it based on our 4 rules so far, and I would encourage you to pause the video and draw it, or attempt to draw it on your own first. We're going to ignore these 2 carbons just because in reality they connect to many other atoms as well. So we're not really considering them here. But for the main atoms that we care about here, this oxygen will have a formal charge of 6 valence minus 6 lone electrons, 1, 2, 3, 4, 5, 6, minus 1 bond. That's going to be minus 1. Carbon here, 4 valence minus 1, 2, 3, 4 bonds. That's 0. And for our nitrogen, 5 valence minus 1, 2, 3, 4 bonds minus 0 lone electrons is plus 1. Sum here is going to be 1 minus 1 plus 0, or 0. That seems to be fine, right? The net formal charge is 0, and the peptide bond overall is uncharged. We should be good. But if we go back to one of the early choices I made when drawing this structure, we see that things might have gone a little differently. So let's draw it again. At this step, the first time, I put carbon's 4th bond here, between it and the nitrogen. But that gave me positive and negative formal charges, and I want to see if I can minimize that. So this time, instead, I'm going to put that bond in between the carbon and the oxygen, like so. Let's finish the structure now. Okay, here we are. If we recalculate formal charge, this time, all formal charges are 0. Now we have a situation, the new Lewis structure does a much better job of minimizing formal charges. Next example, let's revisit carbonic acid, H2CO3. Let's talk about what would have happened if I'd put the double bond between the central carbon of the hydrogen bonded oxygen instead. So if we do that, then recalculate formal charge, we're left with a situation in which we have positive and negative formal charges on these two oxygens instead of the overall 0 formal charge on every atom that we had before. A side-by-side comparison here of the two structures. As you might have noticed, in the carbonic acid structure I just drew, you could have put that double bond between carbon and this oxygen, or the carbon and this other oxygen, because they're exactly equivalent. They both have an H bonded to them. And this gives us a hint at the next topic, which is part 4, resonance structures. So a resonance structure appears wherever there are two roughly equivalent ways to draw a compound. So for example, in the incomplete acetic acid structure I have here, I need to fill up carbon's octet. And there's two bonds I could place. I could either put it here with this oxygen, or equivalently here with this oxygen. And no matter which one I do, the two resulting structures will be equivalent without being exactly the same, since it is technically two different oxygen atoms. Actual resonance structure, which is the more correct overall structure, comes from drawing both of the equivalent structure options and then combining them, which looks a bit like this. But as far as how to actually draw one, let's look at the carbonate ion, which actually comes from the carbonic acid that we talked about earlier. So start with the same 4 steps like normal. Carbon goes in the middle, and it'll be surrounded by our 3 peripheral oxygens. Right. Now we have to decide here where to put carbon's last bond, because it's currently got 6 electrons and needs 2 more to fill its octet. And we're going to do it with bonds because this is carbon. So we could put it here, but equally, we could put it there because it's just a different oxygen. And we can also put it there. So the answer that you might not like to hear, but that is important to know, is that they're all equally correct. So we've actually got to draw each of them. And then to demonstrate that they are equivalent resonance structures, we just draw double-headed arrows in between each one. Then, calculating the formal charge for these, we can see that this oxygen will be 0, the carbon will be 0, and these two will each be -1. And feel free to go through the math on your own. I think at this point it's probably not necessary. So we can see that each resonance form has different oxygens with the negative formal charge. And what this does, on balance, if we consider all of the structures together, is it spreads out this unfavorable negative charge in between the oxygens to make the overall molecule more stable. For the final part of this video, we'll take a look at some of what I call weird Lewis structures and go through how you can apply a rules-based approach to them as well. So first, let's define a weird Lewis structure. To me, a weird Lewis structure is one that either has some nonlinear components, like this benzene here, with its 6-membered ring, or one that contains some more uncommon atoms, like a noble gas, say xenon, or a semi-metal like arsenic. And we'll see structures that have both of these features today. These structures are chaotic and irregular, so the best approach to solving them is to impose rules. Creating some hard rules that we can stick to will take away a lot of the guesswork around these problems and make them a lot less frightening. So here are the rules I've come up with, and then we'll see how to apply them. Rule number 1, using formal charge, find the ideal number of bonds and lone pairs to give each atom a 0 formal charge. Rule 2, if the overall charge in the molecule is not 0, give more electronegative atoms a negative formal charge, and find the number of bonds and lone pairs that gives the atom that formal charge. 3, experiment with different structures while sticking to the correct predetermined number of bonds and lone pairs that you set out for yourself. Now, these rules aren't totally perfect, but they'll give us a really good start. So let's see some examples in action. So for our first example here, we're going to look at S4. It's a bit of a strange molecule, and as you can see here, I've tried to sketch it out already as a linear molecule, and that didn't work because the overall charge that I calculated, which ended up being -2, was not equal to the actual overall charge of 0. So how do we get around this? Well, we can start by applying our rules. Because the overall molecule charge is 0, I'm going to go ahead and assume that the best way to do this is to make each individual atom's formal charge also equal to 0. And let's figure out how to do that. We see it in these two guys, right? When sulfur has 2 bonds and 2 lone pairs, its formal charge will be 0. So all we have to do is construct a structure where each sulfur has 2 bonds and 2 lone pairs. So let's see what that looks like. Give my first guy 2 bonds, 2 lone pairs, and then this one will also have 2 bonds and 2 lone pairs, and I'm intentionally leaving the structure open here because I know that it won't be linear. So I'm expecting some kind of more complicated geometry, and so I'm not going to immediately connect all of the sulfur bonds. So why don't we give another sulfur here, 2 bonds, 2 lone pairs, and it just so happens that our 4th sulfur would fit in perfectly right there. And each one is going to have 2 bonds and 2 lone pairs. So despite how it looks, this is the structure that best follows all of the rules that we've set out for ourselves. This is ASS4. It also happens to have an overall charge of 0. So we're also going to assume that each atom's formal charge is 0. Now, we know how to do this for sulfur already. That's going to be 2 bonds, 2 lone pairs. For arsenic, though, it's only got 5 valence electrons. So let's draw some options here. If we give it 3 lone pairs and a bond, that would be 5 minus 6 lone electrons minus 1 bond, which would be -2. That doesn't work. If we take away a lone pair and give it a second bond, like sulfur, it would be 5 minus 4 lone electrons minus 2 bonds, -1. We're getting closer, but not there yet. Finally, if we take away 1 more lone pair and give it 1 more bond, we'll have 5 minus 2 lone electrons minus 3 bonds. That's going to be 0. So our hard rule now is that each arsenic will need 3 bonds and a lone pair, and each sulfur will need 2 bonds and 2 lone pairs. So how can we arrange these in some kind of presumably non-linear fashion to create this overall structure? Well, let's just experiment a little bit. So start with an arsenic, and why don't we bond it to 3 other arsenics? And then that's all of our arsenics. So I wonder if we can bond these arsenics to each other or to some other sulfurs. So let's try that. Maybe these 2 are bonded. Take away a bond here. Perhaps we can bond these 2 to a sulfur. These can each get a sulfur. And these can be bonded. But it looks like at this point, we're kind of out of bonds, and we've still got 1 lone sulfur remaining. So let's scrap this and try again. But I am going to keep my original arsenic in there. Okay, what if we try bonding it to a sulfur instead? These will each get 1 more bond, so they can maybe all go to different arsenics. And then our only task now is to give each arsenic 2 additional bonds. So what if we did this? We've still got 2 arsenics that are lacking 2 bonds, but the issue is there's nowhere to put those bonds because everything else is full. So back to the drawing board, but I did like this initial structure that we had here. Something like this. Looked good to me. And of course, I know the answer, so I'm kind of cheating. But I'm trying to illustrate here that this really can be an experimental process where you just go by your rules. Okay. Instead of linking to another arsenic, why don't we put another sulfur down here on either side? And then wouldn't it just be perfect if these sulfurs joined up in one last arsenic? So now we've used up all of our atoms, and we have to make some new bonds. And as you can see, these 2 arsenics only have 2 bonds. These two arsenics only have 2 bonds, so why don't we connect them? There's no rules here about how long these bonds can be, because again, this is all 3D geometry. And this final structure, looks kind of like a shield almost, is actually going to be the most correct Lewis structure, because it happens to satisfy all of our rules. So I hope this rules-based approach can be helpful to you in your trickier Lewis structures. Thank you for watching. Have a great day.